Buenas tardes a todos. Me presento para comenzar. Soy Ildefonso Díaz, presidente en este instante de la sección de matemáticas de esta Real Academia. Y en las sesiones de esta tarde vamos a llevar a cabo la segunda reunión, la parte científica de la segunda reunión conjunta entre la Académie de Ciencias de Francia, que están aquí en la sala, y la Real Academia de España de Ciencias. Nuestro primer conferenciante de la tarde es el profesor Juan Luis Vázquez, miembro de esta Real Academia desde el 2014, y formado en la Complutense. A los pocos años se trasladó a la Universidad Autónoma de Madrid, donde ha ocupado su cátedra hasta años recientes, y en la actualidad es profesor emérito por la Universidad Autónoma. Se podría decir muchísimas cosas sobre Juan Luis Vázquez, casi depende del tiempo que tenga uno, pero yo me voy a limitar a un solo detalle, y es que en la historia de España solo ha habido un matemático que haya sido honorado con la distinción de conferenciante plenario de un Congreso Mundial de Matemáticas. Y ese es nuestro conferenciante de hoy, Juan Luis Vázquez, de manera que su reconocimiento internacional por sus libros y artículos es muy bien conocido por todos, de manera que le doy la palabra.
Buenas tardes. Gracias, querido Ildefonso, por la presentación. Gracias a los miembros de la Real Academia de Ciencias. Merci aux membres de l'Académie de Sciences de Paris. C'est un honneur pour moi que j'ai fait des mathématiques en collaboration avec les amis mathématiciens de France depuis les années 70. Et je voudrais aujourd'hui rappeler un peu comment ça a été le début de notre collaboration et en fait l'idée qu'une méthode très simple nous a permis de faire des mathématiques et de réussir à monter quelque chose qui marche bien en Espagne. En fait, Espagne est à présent le pays qui est le 12 du monde en production mathématique. Okay. After this introduction, just to honor the fact that we have his French friends visiting, I will continue in English. Collaboration in Spain in mathematics began in my recalling it around 1970, and before that we knew that France had produced musique moderne and 68. But let me just, decade 70-80 was a time of critical change in Spain, both in society and science, and the country was aimed towards democracy and integration in Europe. And for many of us young graduates, the modernization took the form of contact with France, mainly with France and other countries, but France was next to us. In what respects PDEs and applied mathematics, which is what I was doing, a key moment was the appointment of Jacques Louis Lyons as Doctor Honoris Causa by University Complutense of Madrid in October 76, 1 year after Franco died. The sponsor of this visit was Alberto Dou, was director of the department, and Jacques Lyons' first Spanish student was Antonio Valle, a very influential figure in establishing a permanent contact with France. The word contact is important, and contact with the embassy, French embassy in Madrid, which was very important. Essentially, the strong support of French embassy for Spanish mathematics begins at the time and coincides with these events. So this is just beginning. In fact, for years, Spanish and French mathematicians have actively participated as applicants to French embassy's Acciones Integradas, Action Intégrée, and the Spanish group that benefited the most were those closer to Lyons. But then it was, let's say, a wide movement. For instance, Miguel de Guzmán, who was a very renowned mathematician in Spain, was responsible for the early action intégrée avec Yves Meyer in Paris. This was between 77 and 80. And I participated. It was, for me, one of the first things that I participated. And it was the time before I moved from Complutense to Autónoma. We will see immediately the influence of Jaime Brezis and Philippe Benillan on us. Let me tell you that there were a number of actions intégrées, qui étaient des choses très simples. There were very simple things. You apply to the French embassy, and they have a collaboration scheme, and then University of Santiago used it with Bermúdez de Castro, University of Sevilla used it with Enrique Fernández Cara. We used it in Autónoma, and I did it with Brezis in Paris, and more recently, for instance, University of Malaga with Carlos Pares. So the scheme was simple. And this scheme also allowed to organize things like the Hispano-French School of Numerical Simulation in Physics and Engineering, founded in '84. And this was a very successful scheme that is going on. And since 2002, the name of this school is honors Jacques-Louis Lyons, who has such a strong influence on our Society for Applied Mathematics, SEMA, and many of its members. From the beginning, the French embassy was also supporting this school. And in particular, it supported the two Spano-French conferences on PDEs, held in Madrid in 1982 and Paris '86, with proceedings published by two books by Pittman published in London and edited by Lyons and Diaz. The list of French scholars who visited and collaborated with Madrid universities is impressive, and it was based more or less in this scheme. Lyons, Brezis, Temam, Glowinski, Benillan, Lyons, Pierre-Louis, Duvaux, Raviard, Meyer, Pironneau, Véron, Marie-Françoise Bidot-Véron, Pierre, Sanchez-Palencia, Bardos, Dalamian, Atout, Charot, Cazenave, Galouet, Pertin, Dolbeau. These are the people I knew better, and sorry for many omissions. And the idea is that in order to focus on what really happened in our particular case, let me talk about Brezis and Benillan. In fact, I was not part of the department of functional equations. This was the name for the department of équation à dérivée partielle. But I entered the department in 1976 precisely. And then a crucial event was, for me, was that there was a seminar on nonlinear PDEs at the department, and I was very interested in joining this seminar. And this was the beginning of Nos années sous la grandeur de la France. Je ne savais pas que la grandeur de la France existait pour nous. But that was true. In fact, Brezis and Benillan got involved precisely that year in the scientific orientation of this nonlinear PDE group towards research in the French style. And the period of matureness of this effort of Brezis and Benillan was very short, 76-80. And there were the thesis of the group of students, in fact, 76 Diaz, 79 Herrero and myself, 80 Jose Carrillo, and then in rapid sequence, Francisco Bernis, Miguel Escobedo in Bilbao, Gregorio Diaz, Sisto Alvarez. So these people have been doing PDEs in Madrid before this seminal approach to Brezis and Benillan group. Always involved with his Spanish school, Brezis strongly influenced the work of other Spanish mathematicians later. I mentioned Cabré and Gómez Castro. And these are two typical pictures. One of them is Brezis when he was younger, and unfortunately he died last year. And he was a force of nature, always trying to convince you that the beauty depended on talent and simplicity. He was a student of Lyons, and then the second person who was our friend and mentor was Philippe Benillan, professor in Besançon, who died in 2001. This was a tragedy for us. And he was a student and close collaborator of Brezis. And this is the beginning of our real trips to France. In 1977, we attended the Journée de l'analyse non-linéaire, organized by Brezis by Benny Lang in Besançon. And curiously, that year, there were free elections in Spain. And for many of us, democratic change was very important. But once achieved, we could devote our full effort to science. So this is what we did since 1977. And after the doctoral thesis, time for systematic trips to France took the form of Action Intégrée en Moi Chercheur. And this was very convenient because the funding for this kind of things in Spain was almost non-existent. The beginning of a good organization in Spain began years later, in 1984, 86. So we survived thanks to this contact that was kept. The starting theories, I will not mention the mathematics, just the names and what it is. Brezis wrote a very influential book that all of us studied by heart, Opérateur maximum monotone, a semigroup dans de contraction dans les espaces d'Hilbert. The idea is that if you want to generate a semigroup that represents evolution of a certain process, you study the operator that goes ut equals something or utt equals something. And this something is an operator, functional operator. And the operator, if the operator is maximal monotone, which is a critical name in the literature, then you generate a contraction semigroup. And there is an equivalence. And this was the book that we had to learn it. And there was no mention of this book before Brezis told us to study. Second thing that, in fact, we studied that later, but it was published in 1972, was the thesis of Philippe Benilang, Équation d'évolution dans un espace de Banach quelconque application. What is the difference between the two books? In the first book, les opérateurs sont maximum monotones dans les espaces de Hilbert. In the second book, l'évolution arrive dans un espace de Banach. The idea of Jacques-Louis Lyon's of trying to reduce most of mathematical physics that could be done in this scheme to Hilbert spaces, the typical Hilbert space triad of Jacques-Louis Lyon's, was replaced in the case of Brezis and Benilang by Banach spaces. And the semigroup, instead of being based on operateur maximum monotone, is based on M-accurative operators. So you have to learn something that goes from Hilbert spaces to Banach spaces. In fact, Banach space, a typical Banach space is L1. And they wrote a very influential paper, Benilang, Brezis, and Crandall, in 1975. And I knew this paper line by line. And they say the critical space, L1. And as Brezis told us many times, L1 is not L2. Face it, it's a different game. And it's a window to something that is close to it, and it's close to the evolution equations related to the heat equation, which is measures. If you go L2, is L2 in itself. But in L1, any limit in the weak sense can be a measure. And this is very important. So they opened in 3 books, the Hilbert, the Banach, the idea of going to measures. And in fact, the last book I mentioned is this very famous book by Brezis, Analyse fonctionnelle, Théorie application. He was 83 or so, 10 years later. And the book was so beautifully written, with such a care, such love for the student, that it was a pleasure. I mean, we immediately translated into Spanish. The translation into Spanish was the first done in the rest of the world. And if you are writing a book, you have to take a look at this Brezis book, because I mean you can do it better. I know there is a sense of enjoyment in writing these things. And the idea is combining functional spaces in the classical sense with immediate application to evolution equations and solving PDEs. Okay. So the life with Brezis and Benilang was rich and family way. I mean, they took care of us, which is something that is difficult to find because professors in Paris and now professors in Madrid are very busy. But they took care of us, I don't know why. And they knew lots of things. They were interested in a number of bullets I put here that they knew more or less around that. Brezis knew generation of nonlinear semigroups. I am telling you that. The equations of nonlinear diffusion. It's the heat equation with nonlinearities. And this represents the nonlinear diffusion of solvents in liquids. The existence of role of special self-similar solutions. And this is a different branch that I learned from the Russians, from Barenblatt, the famous Grisha Barenblatt. And then the asymptotic behavior of nonlinear evolution problems is the idea of the evolution is tending to some equilibrium, yes or no? And is the equilibrium immediately obtainable, or do you have to do a renormalization to see it? So this is the law of asymptotic behavior. Then Brezis liked enormously singularities. The idea that some of the solutions of physics are simpler if you go to the limit of some parameter going to infinity. And this was in particular a thing that he developed in the Thomas Fermi model for the atoms, electrostatic model for the atoms. If you tend the atomic number to infinity, there is a singular solution that is easier to calculate. It's a simple model, but if the limits in some senses give you singularities, the singularities represent better in a simpler way things that do not contain the details of the finite calculations. And then there was this, at the time, lots of interest in the theory of solutions which have compass supports and free boundaries representing gases that spread slowly, do not go to infinity like heat equation. And this in particular was interested for the physics of gases at high temperatures, in particular the atomic bomb. And then if you go to the classical theories in France, Brezis was very interested in functional inequalities. I will tell you some. And lately, we come, after diverging in different directions, we came together in the interest for fractional space and non-local operators. So let me go to tell you that Chaim Brezis had a decisive influence in encouraging the students to write the main results clearly and with clear arguments, without neglecting the delicate and necessary time. In fact, he didn't want to sign papers with the students. He wanted the students to do that whole paper, and he could be advisor. And one of the things that happened is that in the 1985, Diaz wrote a book on free boundaries. Nonlinear partial differential equations of free boundaries, which is one of the subjects. And many years later, I wrote a book on porous medium equation, mathematical theory, and this is again in the scheme of things, according to them. One of the things that happened to us is that Chaim and his neighborhood managed to create a community of collaborators and students that allowed for direct contact. We were traveling from place to place every year twice. And then, in that sense, we met people in the friendly basis. And then we changed ideas and we did collaborations. And one of the first tools to do that was what we called at the time European Training and Mobility of Researchers. And I remember the famous director of this training was Bert Pelletier from Leiden, who did that because Brezis asked him to do it. And Diaz, Herrero, and myself were in the Spanish team. In the new century, there was another project that was important. It was the project called Fronts and Interfaces in Science and Technology from 2010 to 2013, where Diaz was the European leader. And he was many times the driving force, but he didn't want to appear. There was this agreement between the two academies that was taken in the morning that led to a historical joint meeting between the two academies held in Paris in May 20 to 24, 2002, and the proceedings were published by RAXA, our journal. Because of this promotion of Spanish mathematics, he was recognized. He was Foreign Academician of the Royal Academy of Sciences in 1999, Doctor Honoris Causa of Autónoma in 2002, Honorary Member of the Société Mathématique Espagnole 2012. So let me tell you one page of mathematics in the Brezis style. How long are you? Okay. So let me tell you one page of mathematics, just to see if this is so difficult. In fact, according to him, if you understand it, it's not so difficult. If you don't understand it, it's difficult. So the idea is that we were interested with Brezis in functional inequalities. The famous ones were Poincaré's inequality, Sobolev inequality, Gallardo-Niremer inequality, but I will present here a collaboration with Chaim in 1997 involving what we call Hardy inequality. And he was so pleased that we wrote a paper together, which is a miracle. So this was the happy day for me. The idea is that we began with an equation that is written here. It's an elliptic equation that implies the Laplacian in a semilinear term lambda f of u, which is a reaction term. And this model that was studied by Lord Kelvin, modeling isothermal ball of gas in gravitational equilibrium. It belongs to the family of Lane-Emden equations, and Professor Gelfand in Moscow studied it in 1959. So the idea is, what do you want to do? I mean, since this is a reaction equation and you look for positive solutions, having zero at the border, maybe there are no solutions. So the idea is, how many solutions you get? There is a parameter, lambda, that helps you. If the parameter is small, reaction is small, and you get a solution. If the parameter is large, reaction is too large, maybe it blows up. So that's the point. Does it blow up or not? Now, it was known that for lambda less than a certain lambda star, there is an energy solution. Energy meaning that the gradient square in the Dirichlet sense is integrable. But what happens for lambda equals lambda star? And then there was a problem. If you go to dimension 9, there is no problem. If you go to dimension 10 or more, you cannot do it. So then we wrote a paper, and the idea of using this model, elliptic model, in the heat equation form had been studied with Ireneo Peral from Autónoma and myself years before, and we discovered that there is a certain ut, which is the evolution, and a certain second member, which is an operator that is not linear. I call it L, but it's not linear. And what you do is you linearize this operator. The Laplacian is already linear, but lambda f, you differentiate, you assume that f is convex and differentiable, and then suppose that it is exponential, you get then this linearized form that represents the stability of the nonlinear form. And if you do the calculation when f is exponential, and the singular solution is minus 2 log x, the parameter critical is 2 and minus 2, you discover that this linearization term here that is variable is c over x squared. Now c over x squared is the dipole coefficient that appears in quantum mechanics. So it is related to Schrödinger equations. And then once you have that, you discover that the stability of a linear operator can depend on the functional inequality related to integrating by parts. So what we wanted, Brezis and myself, was try to understand if the gradient, if the Laplacian that integrated gives gradient square is stronger than the reaction that is u over x squared integrated u square over x squared. So the idea is, what is the trade-off between diffusion of the heat equation and reaction of this Gelman style? And this is for n larger than 2. And at the beginning, the gradient is stronger. So the operator, the good part, which is the Laplacian, wins. And it's an M-magrative operator with a perturbation, you can do the theory. But if you go over 10, it is not true. Because you calculate then in the previous page what happens with lambda star is 2m minus 2. You put it here, and m minus 2 square over 4 is larger than 2m minus 2. So this term is winning, and then you cannot do the calculation. Now, once you resolve this problem, Brezis told me, what happens with the optimal function for this inequality? And it was known that the optimal function does not exist in the whole space, and in bounded domain with zero data. And then he said, but there should be a remainder. And the remainder of these inequalities that have not an optimal function is now very popular. And we discover, after some working, that the remainder is u square. U square is not as strong as u square over x square because of singularity. But this is estimating what happens when you lose the optimality. And the constant that you can calculate is explicit. It is lambda square over r omega square. And r is the first eigenvalue of the Laplacian operator in the unit wall of 2 dimensions. Okay. Yeah. Okay. So after that, I posed to Azua, who was at the time in Autonoma, trying to work with me. This is, I explained his paper, and Azua told me, listen, we can do better, let's work. And then we found that the remainder, instead of calculating a remainder that is u square, you can calculate a remainder that is the W1Q norm of u square. So the derivative can be introduced, but not a derivative that is equivalent to the main term. You cannot beat this one with putting a remainder here. So the Q has to be less than 2. And this was very, we were very lucky. People were interested, and many people work on that. Philippas, Tertikas, Adimurti, Gusu, Moradi, Fam, Marcus, etc. And this is the end of this page of art inequalities. So let me tell you something about linear and nonlinear diffusion. And then the idea is that linear diffusion begins with ut equals lambda Laplacian u, and then the simplest thing is trying to put coefficients. and you still linear. And you put coefficients even in this form, which is non-divergence or uniform divergence. But this is not what we want to do today because we are nonlinear. The nonlinear equation is this monster that is a bit complicated and is still today is not completely understood. So what do? Trying to understand simple cases that have enough mathematics to try to write a book on that, describing what we do. And these two simple cases are the porous medium equation and the P-Laplacian equation. This is the equation, and this is the equation. And they are different because they have the nonlinearities are placed. The Laplacian is still there, divergence of gradient, but there is a difference in the nonlinearity. And you can do the heat equation form, or you can do also the elliptic part. Okay. So first you do the semigroup, and the semigroup in the porous medium works in L1 according to Benny-Lang, and the P-Laplacian case works in L2 according to Brezis I. So they are different. And problem of the characteristics in physics is that for M, which is the nonlinearity larger than 1, you get free boundaries and finite propagation, like in the ionic explosion. While in the case M less than 1, you get fast diffusion and infinite propagation. And there is richness, incredible richness of mathematical analysis. So let me just tell you that this is the figure of the Barenblatt solution in the case of finite propagation. And there is a free boundary here, that is here at certain distance. You can put, the formulas are explicit, and the exponents are explicit, and what you have to prove is that this is the soliton of the evolution in the case M larger than 1. And it is a proof of convergence of an evolution for general data to this fact. Okay. If you go to the case of infinite propagation, M less than 1, the pictures have something very curious. It have a tail. And the tail is not exponential. It's a power tail. Power tails are very important in applications in probability. So these fast diffusion equations are important in power tails. I wrote a book on smoothing decay estimates from nonlinear equations, trying to understand the physics and the mathematics of that. And then we did a lot of relation between functional inequalities and this asymptotic behavior in beautiful papers directed by Jean Dolbeau and Paris Dauphine. And the collaboration was Blanchet, Bonforte, Dolbeau, Grillo, Vázquez. So it's French, Italian, Spanish. And we were very lucky at the time. It was 2010, more or less. And let me tell you that there is another version. With that I will finish. That is, people got very interested around 2005, more or less, in analysis and PDEs, in what we call fractional operators. And the idea is that the fractional operator has anomalous diffusion. It is not Brownian diffusion. You do not spread in the typical way of x equals t1/2. And you do not decay in the tails as a Brownian motion. And then you have to define what is a fractional Laplacian and what means S, the fraction that you are putting. You can do the evolution case, you can do the elliptic case. And this is something that I did in the school of Luis Caffarelli. And you have to define what is the fractional Laplacian. Okay. Fractional Laplacian is curious because it is an operator that was suggested by people in probability. And at the time, there was no connection with analysis. But we are not happy if analysis does not explain things. In fact, the simplest thing we know now of defining the fractional Laplacians that are so popular because of these anomalous diffusions in probability is to use Fourier analysis. If Fourier analysis of the Laplacian is a C2 square. The multiplier of the Laplacian is C square. C is the Fourier variable. In the case of fractional, you put 2s. Now, this is probably difficult to tackle because it's going to Fourier space. If you are nonlinear, it's difficult to go to Fourier space. Oh, there is a formula of the integrals. There is a fractional integral that has a kernel that is singular, and you have to make sense of that. And this was what Marcel Ries did in the 1920s. And then it was discovered the application of Fourier analysis by Stein and Lankoff. But the people in probability want to do random walk. You do random walk and you say that the probability of jumping from site K at time n to site J at time n plus 1 is a certain P Markov probability that does not depend on next neighbor. It goes slowly to infinity with very big influence. You do the calculations and then you find that there is an operator, the generator of this random walk is the fractional Laplacian. There is another extension invented by Caffarelli and Silvestre, and there is still a semigroup formula with Laplace operators. Now, once you have the fractional Laplacian operator with 5 definitions, can you do the analysis of evolution semigroups replacing Laplacian by fractional Laplacian? You can. And in fact, when you try to do it, you begin by trying to look at the energy. The energy of these fractional Laplacians has the same singular operator factor here, only upstairs you can have a square or P. And these are called the Gallardo norms, also Slobodevsky norm, etc. Brezis was very much in love in the last 10 years of his life doing the properties of fractional operators corresponding to these energies. And in fact, if you do the analysis, you discover that for this energy, you have this operator, which is the Laplacian in the version SP. And then what you do is you write the equation. Now, if you write the equation, then you have a semigroup, and you have a theorem of convergence to a soliton. This is the soliton. You will prove that the soliton is there, and in the fractional space, you get the same type of results of the standard Laplacian. And I only wanted to say as conclusion that the influence of French, Italian, Spanish mathematics has been very intense, combining the standard tools of PDEs with the methods of calculus of variations. And outstanding results from entropy inequalities and Weissstein metrics. I will not do it here, but we did a lot. And in particular, the influence of Bacri in Toulouse, Otto in Germany, Del Pino and Dolbeau, Carrillo and Toscani in Italy, Ambrosio. And then in the last 10 years, there has been impressive development of fractional functional spaces. And as I said, Brezis was very interested, and there is a beautiful paper, for instance, by Bourgain, Brezis, and Mironescu, that we studied, all of us. And the theory of free boundaries is in full bloom now. And let me tell you that this was the merit of Luis Caffarelli. But I had the luck of talking once to Benoît Pertam in Laboratoire in Jussieu, who was interested in applying the methods of this porous medium, a version that is called Hill-Shaw, to do asymptotics of mechanical models of tumor growth. And we wrote a paper in 2014 with Quiros, my student and myself, And this was very interesting for the people who were doing mathematical biology. And with that, I will only say that the influence of this collaboration with France was based always on direct contact, focusing on problems that could be important, and trying to prove clear mathematics. And we were very happy, and we hope that we'll continue. La gloire de la France continue si vous voulez. Merci.
Thank you very much, Juan Luis. I don't know if there are some questions to him. Yes, Olivier.
Thank you for this conference. The application to porous media flow is, of course, very well known. But the variety of boundary conditions for porous media is quite large. And what you have done for the Dirichlet condition, does it extend to more complicated boundary conditions?
Yes. In fact, there is a whole community of people trying to do the many branches of the theories. I mean, all of these theories begin with the model, and if the model is successful, begin to branch. And for instance, boundary conditions that are not zero Dirichlet or zero Neumann have been treated by Mazon and Valencia. M-A-Z-O-N, Mazon. And there are many people. I mean, you have to go to the, I can tell you references, many references are in my book, but let me tell you that Mazon was not a student of Brezis, but he was very influenced by Bendilan.
Some other question? If not, I would like to underline the importance of the application, because, for instance, in Netherlands, the school of Pelletier was become interested in the porous media because in Netherlands they win space to the sea by means of just porous media. Yes. And this is why in a very small country there was a very strong team working in porous media equation. But for instance, this equation also arises in population dynamics. Of course. And there are many other applications that are not expected. So
you are right.
This explains that when the mathematics is good, then it's not difficult to find a good application because it's really very hard to work with this equation.
In fact, Brezis told me when I was writing the book, I began in 2001 and finished in 2006, so it took some time. He told me, are you really writing everything about applications? I say, well, maybe it's for mathematics. He says, no. If you know physics, write a number of applications. And in fact, I found it was a beautiful work. 12 applications that are in my book on porous medium, completely described with the references, and one of them is ionized plasma, another is groundwater infiltration like in Holland, another one is petroleum industry, another one is population. There are the Carleman models, there are lots of applications. Yes, yes. And one of the ideas the people, and I mean young students thank me sometimes is, thank you for writing down precise descriptions of the applications. Because otherwise you find it in a book that it describes it in 100 pages. You don't want the 100 pages, you want the 3 pages you wrote. And I try to do as much as possible of applications. In one of the, let me tell you that now the Russians are not collaborating so much. I had lots of help from Moscow.
As a matter of fact, I know that your book on porous media was the best book in the year in mathematics. You told me that.
Yeah, now it is the second because there is a reference book before.
But this is not easy. Okay, we thanks again our lecturer.
Merci. I'm sorry if I was too detailed. Well, I tried to avoid, only hard inequality was important for me.
By the way, Hardy was very happy to don't be applied. But
Okay.
at the end of his life, he get application in genetic with some people of Oxford University. So.
There is a joke that Louis Nierenberg told me. I had a certain friendship with him. He told me, when I was trying to go from geometric problems to more standard PDEs, I talked to Friedrichs, Kurt Friedrichs. And I told him, listen, I have to work with inequalities, I don't like it. And Friedrichs told Nierenberg, listen, Louis, I am earning my life by doing inequalities. Equalities are too difficult.
Yes, okay. We thanks again on lecture. And now we pass to the following one, Olivier. So, our following speaker is Olivier Pironneau, again with a curriculum vitae impossible to be reduced to some words. But let me say you something. Being in France in a very important school like the one of Jacques-Louis Lyons or Robert Dautré, he finished he was finishing his training part in Berkeley. This is why that is difficult to understand. You was very close to very good mathematician. Why you was training finally in Berkeley?
You really want to know?
Well, some
Okay.
short
Yeah.
reason.
No. I registered for PhD with Palus de la Barrière. Do you know him?
Ah, yes.
Of course. No, you don't know Palus de la Barrière? Well, he's a somewhat theoretician, but in mathematics. And he got a job at INRIA as an extra job. But he was asked to be applied. So he chose to be applied to economy.
Uh-huh.
And I had a master in microeconomic, Dobreux type of thing. And when I went to study, after 3 months with him, I told him, okay, what about choosing a topic? And he told me, yes, you choose any topic you want. And what about economy? And he told me, I'm counting on you to learn economy. So I left. I mean, he was supposed to give me a leadership in a topic he didn't know. So, no.
But in any case, let me mention that Professor Pironneau received a lot of prizes. He was a member of the Académie of Science. He was chairman of the Lyons Laboratoire in the Paris 6. And which is important in his career is to be a specialist of very different subjects. Of course, numerical analysis, but also fluid mechanics, and also economics. So finance. So he is able to produce very new results in very different areas. Okay, the title of today is Modeling and Computing the Greenhouse Effect.
Okay, thank you, Ildefonso. So this is a new topic because indeed I like to change topic. And I choose this topic during COVID. I was stuck at home, and Claude Bardos lived just 2 blocks away from me, and it was within a distance. I could go and visit him. And so we decided, what can we do together? And he knew radiative transport. And so that's how I turned to, and we thought, okay, let's use radiative transport and see what we can say about the greenhouse effect. But before I do that, let me mention that I am grateful to Antonio Valle, as you said, first because he brought so many students to INRIA, and I was lucky to be the director of the thesis of Thomas Chacon, Paco Ortego, Carlos Pares, Manuel Castro, and more. And there's super top people. And after that, we kept in contact. So we have very strong contact with the Spanish School of Applied Math. How do I turn this? Yeah. Okay, so I hope I will not be too technical, but I have some equations in my slides. So first of all, being sent here by the Academy, I just want to tell you that we have quite a number of people in the Academy who are experts in related climate topics, and this is a list. Perhaps the closest to what I'm going to talk about is Hervé Letreux. And maybe Laurent Bopp. So you see, an impressive list, and some of them are climato-sceptic. So I will not give names. So what is climate modeling? Because okay, we all know that it's getting hotter. We know that by measurements, by comparing the past climates, and the real only tool, most only tool to know what's going to happen is modeling, numerical simulation. So what is a climate model? A climate model is made of 3 blocks, at least. Understanding the radiative transfer from the sun and from the earth, that's one block. Atmospheric flow, that's essentially meteorology which is used at a much longer time, and currents in the ocean, because the CO2 eventually ends up in the ocean. And the difficulty is that when you put these blocks together, the time scales are very different. Radiative transfer is instantaneous, more or less, at the speed of light. The flow, atmospheric flow, is a matter of days, and ocean is a matter of months. And so even if you master all this, to put them together is not a small thing. And then you have to run them for 100 years. And that's a terribly expensive computer program. So essentially, from the mathematical point of view, I'm going to talk about the first block, so let's see it later. The second block is Navier-Stokes equation with a lot of things in it, like humidity, small particles, ice caps, etc. And the third block is at the moment is done mostly by the shallow water equation on different layers, multiple layer shallow water equation, but more and more they are switching to full Navier-Stokes with salinity, because they want to study, it's very important nowadays to study the vertical motion of the water from cold to hot and to understand the future. You stop me anytime you want to know more. All these flows are turbulent. You know that we don't understand much turbulence.
Let me interrupt you.
Yeah.
Are you telling you in the right-hand side that the ocean is much hotter in the Pacific?
I've taken this from a study, and in that particular day, it was hotter. This is very important. Perhaps we have an expert in chaotic systems. And the basic question is this. You have a chaotic system, Navier-Stokes, but it is forced by the sun. Okay? And so if you run it longer, of course, it's chaotic. But if you take averages, can you extract some information? I think as a mathematical problem, as far as I know, it's not solved. All you can say is that you have inertial variety inertielle, you have attractors, you have... yeah, okay, agreed. So we don't know much, but they use it. It's being used. And this is one of the first major objections to this field, which lacks rigor by many other points, as you will see.
But I guess they use also uncertainty estimates of the averages, etc.
Yeah, well, because the answer is statistics, and you use it in a statistical way, you can apply all the statistical tools like uncertainty quantification for changing the parameters and rare events and so on. But whether it's correct, okay, I you know.
Sorry, but
Wait.
for the recording we need to use the microphone. If someone
okay.
wants to put a question,
Yeah.
please ask me, because otherwise people at home cannot follow the conversation.
No, maybe we can talk again about this after the final slides. So these climate models are open source. It is controlled. You have quite a few of them, and this is a partial list taken from IPCC 24 or something like that. So if you want to be in the race of prediction, you run the test given by IPCC. And so very important climate labs have all their tools. And so in France, we have one which is IPSL is Institut Pierre-Simon Laplace. It's in Paris 6, and they have a full system. Okay, so you can download them. Some of them you can run on a PC like this, but in order to get good result, you need a supercomputer, and usually it runs on Linux, Unix, and so it's open source. You can look into it, but it's not so easy. Now, if you look at the precision of these tools, you know that, whoops, no. You know that the first, I think it's Fourier who attracted the attention of scientists to the problem of change of climate. And then there was Arrhenius in 1860 or something, who it's a pretty incredible study. He computed that if CO2 doubles, the percentage of CO2 in the atmosphere doubled, it would increase the temperature by 4 to 6 degrees. And he did it by hand, just looking at the moon. And okay, so details I don't know.
He was Nobel Prize. He was so intelligent.
Arrhenius is before Nobel.
Arrhenius was Nobel Prize.
Maybe, but much later.
Yes, of course.
Yeah, probably. Okay, maybe. I don't know. Now, now you look at the precision with time. So in 1970, the range was from 1.5 to 4.5. So that corresponds to 3 degrees on the average on each side, 8%, etc. And at the moment, we are at 3%, 1.5 degree on both sides. But if you look at the way it progresses, it's very slow. So in 1950, I would doubt that will be less than 1%. Now, 1%, what do you mean by 1%? Because I compare with 3 degrees compared to 20 degrees average temperature, but in fact, it's in Kelvin. So in Kelvin, it's 200, 300. So, okay. But anyway, progress of the models gets more and more complicated, and the precision doesn't get that much better. And there's worse to that.
So what do you mean by precision? Precision of what?
Precision of the degree of increase of temperature when you double CO2. Okay? I mean, running the climate model. So I think it's in this number is for 2050. Okay. But it's converging. It's converging to something. But look at this paper. This is from the Bulletin of American Meteorological Society. It's not a stupid journal. The art and science of climate modeling tuning. So this is disturbing, because and it's true. What happens is that you take your best student, you give them all the equations of physics, and you tell them to write a climate model. It does not give the right result. You have to tune it. So how do you tune it? You go to Germany, you go to another who is tuned, and you try to change. What they do, they change the model of the chemistry in order to get to simulate a lot the classical test cases which a model should reproduce. So it is disturbing, but at the same time, now that we have AI, we know that models are not complete. You have some, but it's a different tuning, but there's going to be a better tuning now. When a model is not complete, what you do is you take Navier-Stokes equation, you put right-hand side, and you tune the right-hand side with AI. Okay? So this way you conserve energy, and you be able to reproduce the classical test cases. And when a model is not complete, it's kind of, it's not, you know, hurting the good sense, the scientific sense to proceed this way. So now let's go to radiative transfer. So everybody has seen this picture in newspaper and books and so on. So what it says that the sun is coming to the Earth and bringing a lot of heat. The Earth, now be careful, you don't say the Earth gets hot, because the Earth is already hot. And the Earth is hot for two reasons. One is that it's been exposed to the sun for billions of years, and the second is that it was hot when it was formed, and it's still hot. So the Earth being hot is also radiating electromagnetic waves, and they are in the range of infrareds. Okay, so you have visible light on one side, infrared on the other, and this picture has clouds, and it sorts of tell you that if there is no cloud, it doesn't work. So that's not correct. This picture is also working when there is no clouds. So my idea is that can we go from phenomenology to numbers? Okay, just taking this block. So what's a wave? A wave is a Maxwell equation, and the sun is very high. The frequency is 10 to the 14, so it's a big number. So you can take a plane wave. So the first equation is a plane wave, and then you immediately stop, because a plane wave with frequency 10 to the 14, there's nothing you can do with computer. So you have to abandon the Maxwell equation, and you have to go to what they call the radiative transfer equation, which is here. Now this is a terrible equation. It does not seem to have anything to do with the Maxwell equation, and the connection with the Maxwell equation is above. It's a Stokes vector, which contains the intensity of light I, and the rest is polarization. And it's related to plane waves by this matrix, vector. And the first mathematical problem that we found is, how do you go from Maxwell equation to this radiative transfer equation? There is only one paper which I know about this is reference 4 here. And I think it's too bad that mathematicians have spent, so many mathematicians have spent their lives on how to go from Boltzmann equation to Navier-Stokes, and so few of them have spent their life on going from Maxwell to radiative transfer. Radiative transfer equation is essentially Chandrasekhar, and it's done for studying to see what's the temperature in Jupiter or something like that. Okay, so you see it's complex. It has transport, it has absorption, it has scattering, it has a source. The source being that any body at a certain temperature T emits a radiation in all frequencies according to Planck's function. Right, so this is horrible. You don't want to go into that, but not only do you have a very complicated equation, vectorial equation here in dimension space 3 with 2 directions, so dimension 5 plus times 6, plus you do it for all frequencies, so that's 7. You are in dimension 7, but on top of that, if you have, I forgot to say that n is the refractive index, and if you have a medium which changes refractive index, which is exactly the case of the climate because you have air and water, then the transmission condition between air and water is simple with Maxwell equation and horrible with radiative transfer. It's called the Fresnel condition. And here it is. You don't want to read this. It's horrible. But it seems that it's actually the problem is well posed, which is surprising. Okay, so let's simplify a bit. Forget about refractivity, forget about polarization. Take a simple isotopic a simple law for scattering, and you get to the first equation in blue, which says that basically the light is convected in direction omega, and then on the right-hand side, it's you have polarization. What is polarization? Is when the light hits a molecule or an atom. I'm sorry, and then the atom goes into an excited mode, and then it goes back to its normal state, but it emits a photon in another direction. So you have a probability of emitting a photon in direction omega, starting from omega prime. And then the source is the black bodies. And the black bodies, in the case of climate, you have two. You have the temperature of the surface of the Earth, which you don't know. Huh? And you have the temperature of the atmosphere. So if you're at a point, you have to sum the heat coming from the rays coming from the surface and the rays coming from the atmosphere. And so the problem is complicated, but with two of my colleagues, we got this attractive simulation, computer graphics, you can say, but we took the Valley of Chamonix because it's certainly not windy, and Mont Blanc is somewhere in the blue. Blue is, so this is a picture at night, and blue is snow. And we impose that there is snow above 2,500 meters, and you see that what happened, this is a vertical cut here, is that you see the reflection, the heat reflection from the Earth, and so it gets hotter in the center, which is physically sound. Okay, so this is nice, and the way we could do that because of a new tool in computational linear algebra, which is called H matrices. It's a way of compacting matrices, and so that we could we take iterative tools, iterative, it's called the iteration on the source. We compute a new candidate for the light intensity, computed from the old one, multiplied by this, and this at the discrete level becomes a matrix vector multiplication, and we can use this compactification. And so we could do this, it takes an hour, so it's a problem in dimension 7. No, actually 5, because we don't use time.
So the blue part is snow.
Yeah.
Then it depends on the temperature as well, because
yes,
depending on the temperature,
okay,
the glass
this is not perfect.
So it's a coupling in the albedo.
It's not perfect. We impose the snow. We impose the region of snow.
You prefix.
Yeah, but you remember that this is instantaneous.
Yes.
So, so the question is this correct? So how do you know this is correct? Okay, you did your best, but so here it is. We compare with 1D. We do the same thing on a flat ground. On our flat ground, things are 1D. And so it's much easier. And we can, so these are comparison with 1D. And also it contains an information that we can now see the effect of CO2. So we see the effect of CO2. It goes from the solid line to the dot line. So the CO2, in this configuration, you get a greenhouse effect near the ground, but you get a cooling effect at high altitude. So this was rather disturbing to see that CO2 actually cools the atmosphere in high altitude. So we went to see the specialist in IPSL, and they told us, yes, where is it? Yes, the atmosphere is cooling at high altitude because of CO2. And they don't say it too much because journalists wouldn't understand. Well, that's what they told me anyway. And this is a picture of the cooling at 12,000 meters over 40 years. And you see that it definitely cools. Okay? No? Ça va? Bon.
But in fact, when we fly, we hear that the temperature in the...
No, but you don't see the cooling. It's a couple of degrees, and they tell you it's minus 50. So definitely it cools when you go high. I mean, you don't have to take the plane.
This is why this is another model.
You go in the mountain, you know. It actually cools every mountain climber knows that. It cools 1 degree every 100 meters. And that's due to the fact that the pressure is less.
Yes.
Yeah, okay, so in this model, how do we account for CO2? Is the answer. You have, on this side, you have the measurement, you have the Planck curve in black. You have the Planck curve corresponding to the temperature of the sun when it hits the troposphere, the top of the atmosphere. Below, you have the absorption parameter. So the absorption parameter of the atmosphere depends very much on its composition. Because, and you see, it's horribly complicated, and that's because atoms have quantum rays. And you see that CO2, for example, is here important, and here too, and water is also very important. And so by changing this ray, if I put more CO2 in the atmosphere, I will blacken this region. That's how I do it. Okay? For the infrared radiation of the Earth, same story. So the Earth is not exactly a black body, as you can see, but you see here the Planck's curve for the Earth at 21 degree, and you see what the satellite measure. So definitely the satellite measure that everything was absorbed in this region, and only this part could ray. And it corresponds very much to this picture. So in my code, you see so this is the absorption coefficient. So these curves here are reproduced here. And in the region where CO2 is active, I just make the absorption coefficient bigger. And that's how I take into account, I can measure the effect of CO2 with this code. Well, how much time do I have? 10 minutes more?
Yes.
Okay, now you may not want to see the proof of convergence of the algorithm, but let me just say that, first of all, you have a very nice paper by a colleague of yours,
Yes.
Porcio, you know him?
Yes, yes. No, Porcio is from Rome, but
the
Oscar
other one.
López Pouso
López Pouso
is in Santiago de Compostela.
That's right. Okay. And so they took this problem. So this problem is radiative transfer coupled with balance of energy between the temperature and the radiation. Radiation causes. So this is actually the temperature equation that you find in the Navier-Stokes equation, except that all the terms which contains transport and viscosity are taken out because they are very small. And so you're left with this. So they prove existence and uniqueness of this system, and they use accretive operator, which is kind of a
Yes, it's like the maximum monotone of Juan Luis mentioned.
Sophisticated.
In L1. Now in L1.
That's right, sophisticated, let's say. And in fact, I don't want to destroy this beautiful work, but we can actually do the same thing, very simple, by noticing that because of the comment s'appelle le No. Because this is positive, so the solution is positive. What's its name?
Maximum principle.
Maximum principle.
Maximum principle.
So by the maximum principle, if this is positive, then this is positive. And so you take two iterations, you subtract, you see, if this is positive at iteration n, then this is positive at iteration n plus 1. And so I can prove that my sequence is monotone. I can do that the opposite way. So if I start from below, I have an increasing sequence. If I start from above, decreasing sequence. So they are between the two. So you can say that there is a limit. There is at least one solution, let's say. So this proof can be generalized to more complex system. So now we can take into account polarization. So the equations, I don't expect that you can absorb the equations in the case of polarization. This is in 1D. But let's say that you see that maybe you can see something that in the end, I don't need to solve the PDE, I just solve integral equations. I use exponential integrals, and I can convert the problem into a set of integral equations in 1D. It was true in 3D also. So this is convergence that I say. If you start from below or start from above, you see beautiful convergence, only 6 iterations needed. You see the effects of CO2 here. So hotter up to 8,000 meters, and then cooler after between 10,000 and 13,000. Okay, so we had, but I don't want to sell numbers. I want to sell methods. I am not qualified. So back to climate models. In climate model, of course, they have to do the same thing. And I was shocked to see that instead of trying to solve the equations properly, they discretize the integrals with 2 points. Yeah, 2 points. And they call it beautifully the upstream radiation and the downstream radiation. It corresponds to a discretization with an angle of 60 degrees, something like that. Terrible. So I check the precision of this. I check the precision of the scheme with 2 points compared to the full scheme. I got at least 20% error. It's kind of understanding that they need tuning at the end. Because, okay, so there's a good opportunity for more mathematics in climate modeling. And in fact, there is a paper about this error written by some Chinese group. And they found also, an error of at least 10%. They took not 2 quadrature points, but they took 4 quadrature points. And they compare 2 and 4 quadrature points, and even then, they find 10% error. But I think, you know, the problem is the climate modelers are, let's say, limited by their computing capacity. They run at the maximum, so when they have the opportunity, they will fix this, no doubt. I can tell you more about the effect of refractive index. There's an interesting, there's a rather interesting mathematical problem with this equation, because now this equation can have, I mean, we use a lot, you know, ray tracing is basically the method of characteristics. And when you have a refractive index, the rays are curved. And sometimes they just buckle. So what do you mean by this equation if a ray is buckled? Well, actually, physics is a little miraculous. You can give a meaning, but still. Okay. And so what I did is, because I couldn't use the ray tracing, you know, when it looks like this. So I switched to a finite element method, and I still could compute. So you see the rays are curved now. So this is a polarization. This is the intensity, and I can still see the effect of CO2 or NOx or methane. And we still have, not with NOx. NOx actually seems to heat up in all cases, which is a contradiction with what I read. They're supposed to say that it actually cools in all conditions. CO2 definitely heats the lower atmosphere and cools and I think that's more or less what I wanted to say. This is a nice simulation which show you the Fresnel condition. If you have a wave which is concentrated in one direction, coming from this, you can see the one which is reflected and the one which is refracted. This is hard to do. Thank you. That's all.
Thank you very much. So there are some questions.
So this is a very naive question. So these models have been tested on old previous conditions of the atmospheres, and do they predict what we see today?
Oui.
And
you can also predict past weather with these models. Paleoclimates.
These models are reversible?
They are reversible.
Ah.
If you neglect, you have to neglect everything that is diffusive and so on. Or you can, if you want to go past 1 million, you start at 2 million and you go to 1 million, and you adjust the initial conditions, which are not too important because it's chaotic. And so you can either do either way. And you can apply them to Jupiter climates, which they know some about. They have a lot of ways to make sure that these climates are not stupid, these models.
So these models are not stupid.
They're not stupid from, I mean, they reproduce whatever we know about experiments. But they've been tuned to do that. And I have two objections. One is that instead of using very different methods, they all use the same method. They all use the, finite volume methods. They use multi-layer, shallow water. It's all in the same family, and they tune to compare to each other. So they are a bit different, but not that very different. So that's my one objection. And my second objection is that it's not the kind of science I'm used to, right?
I used to work since many years ago on another kind of energy balance model in climate, which work with the mean temperature of the atmosphere, and it's a model that was proposed by Sellers, an American from Princeton University, and a Russian Budiko. And this other model allowed to justify, more or less, the past glaciation that we had in the Earth, by playing also with the solar constant, that is not constant, and it depends on the time. But it's another model in which we simplify this radiative flux, because, for instance, one of the very difficult points in this model is the simulation of clouds.
Yes, definitely.
And how you manage with this kind of problem.
I don't pretend to propose a model that competes with the other ones. But at least clouds have, because they contain water, you can represent cloud in this model by increasing in certain altitude. I did that, and you could see the effect. But I think it's childish. Cloud is very much more complex.
Yes.
Now, to answer the first part of your question, I'm very impressed by some scientists like Fowler.
Fowler, exactly right.
Who they have an impressive capacity of extracting the right important things.
And Gerald North in Texas University, he wrote several books on the energy balance model. Gerald North.
No, I don't know him.
He's very active in this field.
There's a guy in Ireland also, he's very, very good.
But in our model, which play a very important role, is the coalbedo. Just the size of the ice sheet.
The reflectivity.
Exactly, because in the balance,
it's very important.
Very important, very important. And
this
is why
that we can put in that.
And we also coupling the atmospheric mean with the deep ocean. There is another model that couples the atmosphere with the temperature in the deep ocean, which is really very relevant.
That's harder.
Because, yes, but you can simplify the model. There are many. Okay. There is a kind of hierarchy of models. Yeah. And another guy who is working in this is Hasselmann. He received the Nobel Prize.
Is it Japanese?
No, the German. Hasselmann. Nobel Prize in 22.
For climate?
For climate, for just some kind of energy balance models.
I don't know. Okay, I will look at it.
Okay. Well, we thanks again our lecturer. And although it was in the program some short period, I think it's better to follow, because for the recording of the session, it's better to continue. So we'll pass. We shall make a short break to prepare the computer, but we will not use the half an hour. Okay.
Yeah, sure.
next speaker is David Rios Insua. He was training in the Universidad Complutense de Madrid, but then get a full position, permanent position in a new university, la Universidad de Rey Juan Carlos, and now is in the Institute of
Mathematical Sciences.
Mathematical Sciences in the campus of the Autonomous University.
Yep.
He received a lot of prize and he became academician in 2008. Which is characteristic of David is his interdisciplinary application of the tools that he used to apply. He was training in a school founded by his father, by the way. He was also academician. And in fact, your father told me once that he became a specialist in statistics and probability because in the travel of Frechet, when Frechet came to Spain, he proposed to your father, at that time your father was working on analysis with Ray Pasteur. But Frechet tell to your father that in statistics and probability there are many interesting problems, and then your father chose another way and moved to probability and statistics. And that was also the career of David and other brothers and sisters that he has in this field. Well, the title of today is From Cancer Screening to Safe Flying. All intelligent artificial meets the complex real world.
Okay, thanks, Ildefonso. Actually, the actual story was that he wanted to come back to Madrid. He was professor in somewhere in Valladolid, and he was a professor of mathematical analysis. But there was no way to find a position at that time. But there was a position in statistics, so he applied for it, and he became a statistician. Yeah, that's right. Yeah. So thanks for the invitation. So it's a pleasure. I was one of the lucky. I was actually in the picture that Ildefonso showed this morning. I was one of the lucky guys who was in 2002 with Brezis I, and I'm very glad that you were able to come to Madrid. Maybe 23 years later, but I hope that the next one will be sooner. So I'm going to talk on, as Ildefonso said, I'm mostly interested in very complex problems in the real world and try to solve it with mathematics. Now, I must say, with artificial intelligence to get more money from funders. And actually, this is a result of collaboration with tens of people, mainly from our data lab at CSIC, at the National Research Council, and actually some of them are in Paris at Paris Dauphine. Some of them are not human, actually. We're going to see it in a minute. Yeah, okay, so just to set up the scene, I mean, my view, actually served by other people, but my view of AI. So, so this is basically software that is used to generate outputs such as content predictions, recommendations, or decisions with some types of techniques. It's a kind of nice story, at least for a statistician or a Bayesian statistician, that in the version of the law in September 23, they were saying that the sort of three relevant types of techniques were machine learning, logic, and statistics. Interestingly enough, as I said, because they were including Bayesian statistics. But in the final version, probably there was some kind of lobby or something, and they only mentioned machine learning and logic and knowledge-based systems. But basically, why everybody is talking about this is because, well, this is the sort of old-style AI. This is very slow, but well, I'm going to do it like with this. So in the with this one? Oh, okay. Yeah, okay. So basically, this is machine learning. That's let's say it's, statistics made by computer. In this year in the 2010s, deep learning became popular, and the sort of high hype at the moment is because of this type of architectures, which are transformers. And the other thing is, most people believe that there is something like this. So you put a bunch of data into some kind of architecture, some kind of machine, and then you get value. But actually, I mean, the kind of examples that I'm going to talk is more something like this. You need to play a little bit, and then you need to do some data engineering and modeling, and then sometimes you get value. And also you need to respect, that's quite important, legal, ethical, and security issues. And the final sort of setup of scene slide is, this is the LLM rush, which we have had since this paper on attention is all you need, and you can see that the speed of things, how it's running. Okay, so that's a sort of to set up the stage. So what I'm going to do is, as a kind of little stories or short stories, I'm going to provide 5 vignettes, right, on 5 quite complex problems. And basically the story is going to go like, thanks to AI, we are able now to do a few things, and we'll see what things. A little bit of the application domain, what's new mathematically, what are the AI core issues, some sponsors and some publications that we've done on that. So that's basically the story. And the first one is, thanks to AI, we are able now to amalgamate masses of data and expert judgment. And this is a project on the screening for colorectal cancer for the the Horizon Europe mission in cancer, right? And with many, including several French labs. So to set up the issue, this is a third most common cancer. It entails deaths, many deaths, quite an amount of money, and additional problems is that younger people are developing that cancer. If you are able to detect it, then it costs much less money and much less lives. But only 14% of EU citizens susceptible of going through screening programs actually participate on these screening programs. So, as you were mentioning, this is actually could have been. We do it now with machines, but through a standard bibliographic search, that's a kind of knowledge map that we can get from the literature. We did this standard search, then reviewed by experts, and this is we try to relate non-modifiable, modifiable medical conditions and colorectal cancer. That's the kind of thing. But then we had access to from Fundación Quirón, a large database with 2 million people, etc. And then we complement. So the black is, let's say, standard medical knowledge. With red, we complement it with data. That's one of the things that. And this is it was quite useful to predict cancer, provide risk maps, etc. But the interesting thing is one thing that I would like to convey is that we want to do this to make to support decisions, right? And in particular, we want to support screening decisions. That's the graph that we had before, the model, and we incorporate decisions like what type of screening method, if it gives positive, should we provide a colonoscopy, and the idea is that we want to provide a sort of optimal screening approach and taking into account various types of costs, the comfort, and the information that this device provides, right? With these kind of models, we can provide personalized screening. That's the sort of most important for our project is we can benchmark new screening devices. But interestingly, as a side issue, we can assess and screening programs and design new programs. I'm putting there the current, I think in France it's the same, or it's very similar. Basically, while you are between 50 and 70, you receive a letter every 2 years saying, come to do the invitation. You go through some test which is called FIT, regardless of your features. And if you are not in that age range, you receive no letter. But actually, this is the approach that it should be followed. So if the probability is smaller than a certain threshold, which depends on the resources available, you should receive no letter. If it's in between, if it's between certain two levels, you would do fit. But if the probability estimated given your features, you should receive another type of and with this, I mean, we would catch more cases, and well, that should be, I mean that would be beneficial for society. Okay. So the second, the second example, the second thing that we can do is large-scale forecasting and decision-making. And the example here is now designing the Spanish state's aviation safety aviation plan. Actually, this is kind of nice to do it here because it's a project developed within the Académie, and you'll see the interesting consequences. So that's the sort of system. In Spain, flying in Spain, there's about 2.5 million operations, 50 airports. Well, it's really huge. And the important thing for us is that there's 88 types of occurrences that interest to the authorities, like a bird hitting an airplane or two planes crashes, etc. Okay, with 8 consequences of interest. So again, it's a sort of complex problem. Examples include the number of people dying, but also things like the image of a country where we basically live on tourism, so it's quite important. Yeah, 40 accidents in all types of airplanes, right? Yeah. Accident is defined as an incident in which people die or the aircraft is destroyed, right? But well, there's 2.5 million, right? So, and 30,000 incidents. So examples are like something like this. So this is pretty bad. This appears in the news. It happens in Tokyo, I think last year. Some are really bad, but some are not. Sorry. Like this, yeah. We have the Los Rodeos in the 70s. Yeah.
You can fly to Paris.
Yeah. Yes, that's right. So some are bad, some entail people dying, etc. So the kind of structure that we consider, this is a simplified version, but basically we need to make decisions. We have resources. In this case, our inspection resources that the agency has. And I put here just 2 of the incidents, but imagine that there's 88 like this, so it's a quite complex model. The things that we must take into account, we must forecast the number of operations, number of occurrences, then each type of occurrence, depending on the degree or severity, it could have fatalities, etc. Okay, so this is a pretty complex problem. And sort of the new thing is the kind of models that we use. And we use a model to forecast the operations. That's we call it in statistics. We call this dynamic linear models. We use a dynamic linear model for the rate, and then we make some kind of nonlinear transformation, and this goes time over time, right? Yeah.
You want to optimize what?
Yeah. The allocation of inspection. So the agency has basically so if it inspects more intensely some company or some airport or some operator, so you expect them to be, to perform it more safely, etc. Right? So that's a huge, more than 2,000 forecasting models, which you can, I mean, by person, you cannot do it, and you need machines. You need to buy to do some machine learning approach to learn them. So that was quite complex, and we had to devise this system. That's the kind of that when we did. So that was the forecast in blue. The forecast if the agency maintained their current policy at that time, and that was what we forecast with our policy, the red one. So that means less cost. So this means good. And when they implemented it, we had a success. I mean, it was the kind of validation that I think you asked before. So black are the predictive intervals. Should they have preserved their policies? White are our predictive intervals, and you can see that we captured the. I mean, they implemented the policies that They implemented the policies that that we suggested, and I mean that was quite successful. That as a side issue, this is like 800 million euros of safety of safes every year, and as a comparison, the whole CSIC, the budget, the annual budget is 800 million. So that was quite successful. Okay. The third thing that we can, good thing that we can do with AI is accelerating processes that previously took long years. And the sort of prime example is producing new drugs for various things. And I'm going to talk discovering new drugs for Alzheimer's disease. And that's, again, supported by the government and with a startup created at ISEMAT. Okay, so basically, a drug development process is like 12 years. Most of the molecules don't get approval in the end. The process is demanding increasing animal use, and the chemical space is huge. It's 10 to the power of 60 molecules. So how do you explore, basically? And the process that we follow is we start with an LLM, in theory thought for language. But what we do is we use, rather than predicting words, we use it to predict molecules, right? And what we make is we need to sort of represent the molecules in some ways. There's various representations. We use some which is selfies. It's called selfies, right? And what we do is the tokens that we use is just each symbol, right? This is kind of nice because it's it's kind of romantic because it's the you probably heard that the LLMs are basically autoregressive now models, right? And autoregressive models, Markov chains, were basically invented by Markov to forecast each letter or the next letter. So that's the same idea. This with words that it doesn't work, right? But here in chemistry is very important because a symbol like a C, a carbon, it's super meaningful, right? So with this, we train this with this database. And we have something which we call ChemGPT for molecule generations. So we have a mechanism to generate new molecules. This is fine, but these molecules could be crazy. So what we do is incorporate a reinforcement learning approach. And basically what we want is a property which chemists call docking. So they want a molecule which docks in what they call protein pockets. So there's, for Alzheimer, for example, there are protein pockets which are well designed, right? So the idea is that we have a mechanism to, we have a forecasting model which says, given this molecule, what is the sort of degree that this will dock in this pocket? So with an optimization model, a PPO model, we developed this at ChemGPT. For molecule generation that is now, these are not crazy molecules, but molecules that are good at that property. And well, assessed with it goes quite well with DrugGPT, Chem2Mol, etc. And then it's not just reinforcement learning, but also constrained reinforcement learning, so we put some constraints to get some good properties, and moreover we can do with multiple objectives. So we can try to be good at linking or docking nicely in several pockets, which is even should be better. So that's the molecule that the best molecule that we found. That was synthesized in lab in the lab. It seemed that it was stable. It's non-toxic. It adheres nicely to the. This is the pocket. This is the pocket. One of the pockets for Alzheimer's disease. It's biologically active, so this is a promising molecule that, I mean, maybe some pharmaceutical company will use at some point or will study in more detail. But the idea is that a super long project, a super long activity, we have done in a few months. Okay. And the fourth good thing is radically new technologies that were a dream a few years ago, and these are social robots that we are developing to support autism therapists. And I can say this is a dream because I failed. I went bankruptcy like 3 years ago. So we did that one. We sold 3,000 of our robots in 26 countries, and that's a sort of one of the success that we, well, thanks to his mother and our robot, this kid with Juanito learned to speak, but we failed. So at that time, that was like 5 years ago, chips were not so powerful, NLP vision was not so developed, and we were also a bit unfocused on what we were looking. And since then, well, there's now improved single board computers with AI facilities, NLP, you know all about it, improved vision tools, improved multi-agent reinforcement learning, and the government has introduced an excellent AI program which we have taken advantage. So the idea is to put into this machine some kind of emotional element to build a better interface with users, and this could be an excellent tool. I mean, our hypothesis is that this could be an excellent idea to interact with certain users, especially with kids with autism. The social elements are also important, and basically that's the kind of mathematics that are going within the. Basically, the robots will operate with certain models under normal circumstances, and sometimes exceptions arise, and they need to perform interventions until normal circumstances. Right.
I'm not sure I understand. The machine is discussing with the kid.
I will explain a little bit more, but one of the things is when it will support in this domain, it will support the therapist. So the therapist says, "I want to play to what kind of color is this," and the robot can work. Can show a color and tell me what color is it. The kid will tell, etc. The idea is to build an interaction with a simpler object. I mean, we are very complex. Our faces are very complex for persons with autism. That this will simpler and the interaction will be better. That's the hypothesis. So in just what you were in this sort of very simple experiment, the idea is that the robot will implement the games, will track progress, encourage criticisms. It can speak, etc. It will introduce some randomness because otherwise it would be too boring. And then exceptions could be other orders from the therapist or demands from the child, and it could start speaking, or sounds, images, emotional changes, etc., etc. So these are the kind of things that you can do with sensors. You can listen, understand, respond, all these kind of things. And that's the sort of our plan. So for the first one will be pre-programmed therapies with some randomization, and if exceptions occur, we undertake a fast optimization to improve if how do you say? Yeah, in the medium term, I mean, life here is pre-programmed, right? Here we would introduce reinforcement learning policies to sort of develop the life of this robot, and in the long term, I mean, we dream of robots cooperating or competing, and we would use we are planning to use multi-agent reinforcement learning. I mean, that's the kind of models that we use. The most interesting or different part is the emotional affective elements that we introduce to modify relatively standard expected utility optimization models, right? Well, that's some idea. And this is the robot that I mean, this was our old robot. This is the new one that we are. Maybe next year, if we have a next encounter, we can show it.
He will do the conference for you.
Yeah. We could make a Spanish robots and French robots academicians, right? Yeah. So.
Making war.
Sorry.
Making a war.
No. Well, actually, that's a good point. That's a good point because that's the sort of. That's actually the area in which we work more now on highly insecure AI. And the idea is that we need to make those systems more secure. AXA, for example, has been sponsored this for a while. And the idea is this is the World Economic Forum. That's Benjos for the conference that it was in Paris. These are actually Académie's activities. So the AI in healthcare and the strategic crisis management are talking about basically insecure AI, and this is the European law, the recent European law. The idea is that these models are insecure with little perturbations in the data. I mean, with clean data, the systems work nicely. Accuracies of 99%. With not so clean data, attack data, the performance goes down quite quickly. So it works nicely because actually it sounds like a sort of difficult problem to predict handwritten things, but it's now a commodity and it's actually a very easy problem. But if you perturb them, you can see that why the systems get confused. So for this, we are developing this adversarial risk analysis approach that we developed with AXA. So that's some gratitude to France because they allowed us to do that kind of things. But basically, here we are representing a sort of a standard classification problem, a problem of classification when there is an attacker, right? And what we do is basically try to forecast what the bad guy is doing. And once we get a forecast, then we make a standardization problem. So here is I put an example from images, but this is from text. And basically, you can see that this is a number of different classifiers, machine learning classifiers, that perform reasonably well in, I believe it's a recommending problem. But if you can see that with attack data, the performance goes down quite a lot, right? And with this approach, with this type of approach, we recover the performance and even get a little bit better in some cases because there is some kind of regularization effect. But this is very expensive to run online. And for that, we do, the standard is called adversarial training, and we do our ACRA training. There's some details, and you can read the papers, but let me show you. Here is one example of how the performance of a sort of standard classifier goes down, right? The blue and purple are the sort of two standards, which are called adversarial training, AT and ALP, which is adversarial logic pairing. And this is our approach, which is the yellow one, which is, I mean, for clean data, we do worse, slightly worse, but we are much more robust. So that's good. Finally, finished. So there's too much of a hype. I don't think so, because this is going to stay forever. I mean, there's some sentences which are excessive. For example, AI is the end of Homo sapiens, which is false. But there's many important issues, ethical issues, security, deceptive alignment, which need to be confronted for regulation, at least from a European perspective. And some final messages. Well, there's life beyond LLMs and transformers, right, and beyond AI, I would say. The key role of mathematics to sort of go ahead. It's not like black boxes, etc. Data and expert judgment. I mean, it's not just a matter of data, but you need expert judgment to model it, etc. And having said that, well, there's an unrealized potential of Bayesian methods within current AI as it's conceived. Nothing else, nothing more, and thank you.
Thank you very much. Thank you very much, David. Very interesting talk. Some question?
I'm not too sure I understood what kind of neural network you used. You use commercially available neural network, or you wrote everything?
In some of them, yes. In some of them,
not, yes. And how big are they?
Pardon?
How many neurons?
I mean, the neural network, it's GPT-2, which is, I mean, the current generation is GPT-4, but because it's open access, so that's the one that we have.
Okay, but so you run it on their computer. You don't bring it to your computer, do you?
No, we use it. I mean, it's available open.
Yeah, that's right.
And we use it in one of the HPC machines that we have access to.
So that's expensive.
Yeah, but it's worth. Yeah, I know. It's worth because you.
800 million.
And sorry, just a second. And for the robots, we use actually an NVIDIA Jetson, and we need to use a tiny LLM, right? So it's a sort of small version, but it's sufficient to speak in, I mean, in a sort of informal conversations. That's sufficient.
Well, thank you very much for a very interesting talk, David. I enjoyed it a lot. I was very curious for the example that you have shown of generating new molecules using a large language model. Because I don't understand exactly how do you do the word embedding. So how you transfer if molecule to the large space in such a, I mean, this large space, if they are too close, they have similar properties and so on.
Yeah, so first we use a molecular representation. There's various ones, and I mentioned selfies, there's smiles, etc. And the important thing is the sort of the tokenization. So I mean, in language, in words, you have to break the words in pieces, right? But in this domain, you just need to use one symbol per one symbol. So you use a C for carbon, and this is very meaningful, and this is sufficient to obtain good things.
I am not sure I understand it right, because as far as I know, the properties of a molecule depend not only of having, let's say, carbon, oxygen or nitrogen, but of the position in the space. So the position, the properties of the depends a lot on the position. So how do you transfer this information? Or are there a procedure that you are using that it has been invented, or are you doing because that's very hard to do. How to do a good embedding. I mean, we know how to do in words after a lot of training and transformers and everything that you have explained. But in molecules, I am not expert at all. So I have a lot of curiosity how the embedding is doing. Thank you.
It's something. Well, there's some embeddings that are similar. You need to take into account the sort of the atoms, right? But also you need to take into account the links. I don't know the word in English. Roughly, you use a sort of let's call it vocabulary of 112. With 112 symbols, you can represent all of them, and it's in this case is simpler, right?
Yes, Juan Luis.
Yeah, in the case of proteins, it's very important the folding, right?
Yeah.
The way they fold. It is completely complicated. Can you do it easily?
I mean, we use this selfies representation. I mean, there's at least five or six types of representation. But this selfies representation takes into account the links, and I mean, it basically the 3D it's converted into to the structure, to dimensional structure, and then the this selfish representation makes it possible that the sort of newly generated molecules make chemical sense, right?
Okay, we thank again our lecturer and pass to the last one of the session that will be in charge by Bertrand Maury from the French Académie of Science. Bertrand was training in the École Polytechnique, and after that he moved to Houston, spending some time with Glowinski, and after that he was working in the Pierre and Marie Curie University, the former Paris 6, in the Laboratoire Jacques-Louis Lyons, and finally he found a permanent position in the Orsay University in Sade, Paris Sade. He received several prizes, especially the Médaille d'Argent du CNRS, and very recently he became charger of the journal, the Conrandi of the Académie des Sciences de Mathématiques. His talk today will be crowd motion models of the gradient flow type.
Thank you very much. Thank you for the invitation. I'm very happy to be here and very proud also. Yes, I like to talk about kind of exotic subject. Let me warn you that I will talk about traditional modeling process and nothing to do. I said because some people have started to use AI type methods to model crowd motion. But that will be, as you will see, quite old-fashioned modeling. Let me start with an animation with experimental data. They have been actually filmed in Spain, in Navarra, as my colleague Iker Suriguel. This is one of the phenomena I would like to try to model, try to explain. Modeling is not only forecast, but also try to understand and explain. And this is the simple fact that when you have many people, they want to rush out a door. When there are too many of them, it goes less quickly. Simply, it's the capacity drop. This is an animation that has been it. Obviously, it would be much better if everything was well organized. The people were told to rush out of the room. The second effect, that is a little bit more subtle, is the fact that when you lower the competitiveness, because you ask people to be more polite, it actually works better. Usually it's called in the reverse side, faster is slower effect, meaning that on the right-hand side, people are some kind of aggressive, they try to go very quickly, and on the left-hand side, they are more polite, they go more slowly. And actually what you expect, well, some kind of paradoxical effect, the fact that it goes smoother and better where people go, well, it's worse when people go faster, as you may expect. So I will show again that this video, but you can believe me that it gets quicker on the left when people go slowly. So they are, I will not give you a large overview of social force model. They have been introduced mainly by physicists about 10, 20 or 30 years ago. The first one, what was called the social force model by Dirk Helbing, a physicist in Switzerland, is based on the assumption that people are considered like particles, like physical particles with a mass, and you write Newton laws, and the important term is this: I, capital U, is the desired velocity, the velocity that the guy I would like to have would he be alone, and you have a relaxation term toward this UI, and you also have interaction terms. Basically, you want to model the fact that when you don't know people, you don't want to be too close to them, basically. And it has been studied actually by some American sociologists. It's very interesting to say it depends on the culture, and I don't know about Spanish, but you can really measure that. For example, French people, you have like 83 centimeters, that is the right distance. Because sometimes when you meet people, you feel kind of awkward because they do not have the same distance. They are too close to you or too far away. Yeah, it can. Yeah, and you have to know that when you go to a country. I think it's important. So, and let me just say, if you have, that may be nice for students. I make many student projects with that. We made with my colleague Sylvain for Python or open source library, and most of the computation I'm going to show are made with that. So I'm not selling anything. It's open source. This is the kind of thing that you get when people try to evacuate a room, so it looks nice. You have another class of models that are also borrowed from physics, and more specifically statistical physics. It's called cellular automata. Basically, you are some kind of a grid, a chessboard, when you have 1 or 0 people in each square, and you have some evolution rules, stochastic evolution rules. Basically, you have that guide, for example, can go here, here, and here. You have 4 possibilities, and you have probabilities that are biased in the direction of the desired velocity. And it looks quite crude, but actually it's used. You have commercial software based on this approach. That's quite a bit surprising, but it's used in practice, and it's difficult to tune out, but actually it gives reasonable results in simple situation at least. Okay, so now let me forget what was proposed. Now we tried to introduce a model. What we had in mind is to introduce a model without parameters. All these models, they have many parameters actually. They are hidden, but here you have 3 or 4 parameters. You have the mass, you have this typical time, and here also to define the probabilities. You have many parameters that, and I would like to show you an approach that will give some kind of model without parameters that you like as mathematicians. So it's based on a gradient flow, so it's a very basic, sorry for the simplicity of the slide, but the starting point is a gradient flow in a Hilbert space or Euclidean. Just you are given a smooth functional, psi, say C2 functional, say if you are in a finite dimensional space. And well, it does not necessarily to be C2, just C1, and then you can define, even if you do not have uniqueness. And you just go in the steepest descent direction according to this functional. And the example I have, this is close to Spain. I think you imagine a drop of water that flows down the isolines of the altitude going this. So this is the principle. And the idea is to apply that to crowd motion. Here, it's taken from Centre Pompidou. It was an exhibition that we took the plan and just we computed these isolines. Those isolines corresponds to the distance to the exits, geodesic distance, meaning that it takes into account the walls, for example. So if you are someone here, the color corresponds to his distance to the exit, and if that guy is alone, it's going to go to flow along. Oh, I missed one slide. Sorry, you have to imagine that it will go that way, like the drop of water, and go in this direction. So this is the gradient flow for a single person. Of course, it gets a bit more complicated if you have hundreds of people. Of course, if each follows its gradient flow, it's not going to work. You're going to have congestion, etc. So you want to generalize this approach to this. So the idea is simply to consider that, like you have many people, you have a common radius, and this is the feasible set. You do not want overlapping, so you want the distance to remain non-negative. And you assume, it's not necessary, but here we will assume that the individual velocity only depends on the position you are at. The people have no personality, you can't interchange them. And actually the desired velocity of I only depends on their position, and it's the gradient of the distance function to the exits. So it corresponds to the image I gave you. And so you can define a global dissatisfaction function, meaning that what quantifies the dissatisfaction of the crowd. Basically, when you want to evacuate Rome, it's reasonable to consider that the distance to the exit corresponds to your dissatisfaction that you want to lower. And you are simply going to sum all this dissatisfaction, and then you add this term that is what's called the indicatrix function, that is plus infinity when you do not meet the constraint, it is 0 when you do meet it. It simply prevents the configuration to violate the constraint. So it's very simple to write, but you will see that it's not so simple to study, but it's quite natural to see it's just a way to account for the constraint, non-overlapping constraint, and the question is whether it's possible to define a gradient flow for this function. Of course, this is not exactly differentiable, it's not even continuous and not even finite, but there are tools for that, and one tool that we used a lot was the work by Jean-Jacques Moreau, who you may have, I guess, have heard about. This was in the Brezis galaxy at some time. It's a very nice thing. It was written, actually it was inspired, motivated by application elasticity and plasticity, but it was presented in a very abstract way. You have a collection of convex sets, depending on the time parameter, and basically that's not the way he presented it, that's the way I like to present it, because the equation it's bizarre, and I think the best way to get to the equation is to consider the numerical scheme and to get from the numerical scheme to the equation. That sounds bizarre, but it's the best way to understand it. And so the principle you want to model is the points, you want to move it as little as possible. Basically, if the point doesn't have to move, it will stay, it will remain still. And it has to stay in k of t. So basically, you can imagine this experiment. You will not see it, but you can imagine it. You take a point like that, a little, and you take a glass, and you put it here, and you move it. So you don't see it, but you imagine. And OK, when you are in the glass, nothing happens. And then it's swept by the boundary of the glass. And this is the convex, closed convex set in my infinite dimension, possibly infinite dimensional Hilbert space. And the algorithm that was proposed, called catching up algorithm, is like a prediction correction algorithm. You have a time step, and you move. You have the previous position, you move the convex set, and then you project. It's a closed convex set, you project, and then you get a discrete trajectory. You can interpolate to get a continuous trajectory, and you can have tau go to 0. It's natural to expect that it converges through something. What can you write? Oh, this is an example, just to, this is a proper, this is a computation, what you can expect in a very simple case. Let me just say a little bit of convex analysis for those who might not be familiar to that. When you have a convex set, so basically what I wrote, it's the next position is the projection of the previous one. And you have an equivalence that this is the projection if and only if this vectors lies in what is called the outward normal cone. In the case when you have a smooth boundary, simply a half line, and here it can be a bit more complicated if you have a singular point on the boundary, but it belongs to it and it's an equivalence, and it's also the subdifferential of the indicatrix function, this bizarre function. And just to say, I'm not going to go too deep in convex analysis, but this subdifferential is a very nice way. I don't know who introduced it, but that clearly it was very popular in the 70s, and Brezis worked a lot on that. When you have a function, say from R to R, it generalized the notion of derivative. Here, when the curve is smooth, basically is the set of slopes of lines that stays below, that remain below the graph. For convex function, it can be generalized to non-convex, but here I only deal with convex. When you have a point like that, here you have infinitely many possible slope, and then you get an interval. So you have a multi-valued functional, and it can be generalized to function that may take the value plus infinity. So it leads to this equation. It actually looks like the time derivative of a continuous equation, and this is the way he wrote it, and it was published actually in the note au compte rendu de l'Académie des Sciences. I would say in 70 something, 70, oh, it's this paper, 73, so it's very...
I think that was Rockefeller who introduced
the notion of...
multivalued...
yeah, the subdifferential, yeah, that's right, yeah. And let me, I just added this a few minutes ago that it's actually quite related to the notion of maximal monotone operator by Brezis. And it was not expected. I didn't work on that, but I wanted to...
The time was the same, 71, 72.
Yeah, it's about the, yeah. And actually the crowd motion model fit in some way in this sort of framework, at least. If you consider the global functional, you can write that at the gradient flow, or you can write that in a Brezis spirit, like a differential inclusion. Let me just say that actually it took 1 or 2 PhD theses to actually fit into the framework, because this is not maximal monotone exactly, for a very simple reason. It's just the set of feasible configuration is not convex. When you have two balls, two disks that are not supposed to overlap, this set is not convex. You have this configuration, this one, the average between both, you validate the constraint. So actually this is not a subdifferential in a proper sense, and it's not maximal monotone. So there is some work to do. I will not, it's a bit technical and not very interesting, but it took at least 1.5 years to a PhD student to actually have it work. And you have another formulation, perhaps simpler. It's actually the way the first idea had this form. You just have a cone of feasible velocity. Basically, it means that when you have two particles that touch, they cannot overlap more. So it's a condition of the relative velocity of the two particles, the two grains or the two people. Okay, so if you plug that, it's not so simple, but we introduce an algorithm just to project, to make the catching up algorithm, and this is the kind of thing that you get. So you handle the constraints, and here we exaggerate it a bit by having very fat people like that, just to have some jams, because we wanted to have something a bit spectacular. But of course, we didn't show that to the people who were organizing the exhibition. But it's interesting, and I will come back to that, the fact that it is able to reproduce these jams, which are they realistic? Actually, I will come back to that. It seems that they are. So this is just another simulation with a little bit of social forces, the fact that people do not want to get too close to each other, just to show that you can also add some psychological ingredient to have something a bit more realistic. Okay, so let me come back to the evacuation process and show you an evacuation of, let me check the time, of with a single exit that is about 2.5 times the people. So theoretically, it's possible to evacuate everybody. What you have here, I don't know if you see it, the lines, they correspond to constraints, and actually to handle the constraint, you use Lagrange multiplier, and those corresponds to interaction forces between grains, between people, something that you feel when you are in the metro in Paris, and that's what this represents. And you see that it evolves very quickly in time, and you have force arches, and this is what is a bit surprising here. There is no psychology at all. It's a straight computation of what I showed you, so there is no parameter. Also, of course, it's not Spielberg, but it looks a bit realistic, as if some people were hesitating at the there is nothing, no ingredient in this direction, yet you recover some kind of very, they say, stop-and-go waves that are observed actually in practice and can be measured. So what happens when you go, it takes a bit long, and sometimes you get something that is fully jammed, actually. And when we first got that, we said, okay, there is probably a problem in the code, and we even showed this to people used to crowd motion modeling. That this told us, okay, you should not. And I understood after this that the other model, they didn't find jams. But the question is, does this exist? Is this really stable or just metastable? Perhaps it's just it's not completely clear. And I just wanted to know. I don't know if some people are. I think but the children should close their eyes. It's but you can find it on the net. So yeah, even with the title, you could imagine where does it come from. So let me show you. So it's a bit wild at the beginning, but people are pushed and very excited, and they arrive at some place when there is a very large door, and you will see what happens, which is a bit surprising. Yeah. So it's a bit different from the main. Here you have you have a very large door, and everything is blocked, and people are very, very motivated, and they push. And so you have something like this with desired velocities that concentrates toward the door, and so it's something that you can observe. And what is interesting is that you can also, I told about the faster with slower effect. When people reduce their speed, actually it goes faster, and something you can recover by considering some kind of social ingredients. You just consider that you have some parameters. So for each I, for each individual, there is a coefficient that it's 1 in the previous model, but you are supposed to, you can reduce it if you decide to take upon you to forget that you are important. Basically, if you are jammed, you cannot go forward. You stop pushing, and you just forget about yourself. Meaning, in some way, it's very civilized. If you have your beta I go to 0, it means that you do not participate in the global dissatisfaction. You forget that you are dissatisfied. Okay, so in some way, you are very civilized. And what happens is the following. I started from the previous jam, and then I run this program, meaning that when you do not move, whereas you would like to move, you reduce your beta I, okay, dynamically. What happens is the following. Here is the jam, very stable jam, and then the model starts, and immediately it starts to go. So here people go much slower, and it goes much faster. Well, it's not difficult to go faster than 0. But actually, so I'm not saying that it's realistic, and you find also something that can be observed in practice when you are in Paris, for example, Châtelet. It's better to be in the center line, because that guy here is going to go out at the end. And okay, so a very simple model without any parameters is capable of reproducing these effects. Okay, and this, to get back to this video I had, we can reproduce. I'm not saying that this is a straight modeling person per person of what happens here, just qualitatively. You find that here we have uncivilized people, and here we have more civilized people which adapt their velocity. They have a cone of vision, they adapt, they are polite basically, they do not push, and it goes actually faster, like in the experimental setting. It's not so spectacular, but it's significant at least. Okay. I would like, how much time do I have? So like 20 or 15? Yeah. I'd like to say a few words on, excuse me?
10 minutes.
10? Okay. So let me go a bit quickly on the macroscopic setting. So it's completely, well, different. You would like to have macroscopic model, like a fluid mechanics, a model in fluid mechanics. And the model is very easy to write, actually. You consider that the density, the crowd is described by a density rho. You have a distance to the exit. You have a constraint space. I still keep the notation K, but now it's I mixed measures in density. Actually, rho represents a density, the density of probability measure or a measure of certain mass. And with the constraint that it cannot go below 1, okay? That is the maximum. In practice, that would be like 6 or 7 people per square meter. And you write the global dissatisfaction exactly as before, and you integrate rho against the distance d, so you have a global dissatisfaction, and then you add this indicatrix function that is plus infinity where the constraint is violated. So it's very simple to write. And you write that under quote because in which sense can you give to this equation? That's not very clear. I don't know if it's clear for you, but I have to say that it took me about 4 years to understand what sense could be given to this equation. With some discussion with a certain Cédric Villani and also Alessio Figali, a long time before they get there, but they were still already working on optimal transportation. But this was not so easy. So I'm not to go in the details. I just would like to say something that is very basic and also I think very important. So when you have a measure, a functional that depends on a measure like this linear functional, you have 2 ways to differentiate with respect to probability measure, probability density. First one, it can be called Eulerian. I don't know if you know this expression. It comes from fluid mechanics. It's basically vertical. You take at some point and then you change what happens locally. And you have vertical, you have h that has a 0 mean, and then you add it and you perturb by adding. That is the normal way to think when you do PDE. We will live in a Eulerian standpoint. But there is another way to move probability, is to move it horizontally, like really to move like you would move sand. So it has a flavor of optimal transportation. It's related to that. So you consider, for example, velocity field, and you move horizontally, and then you can differentiate the functional, and by a change of variable, you find something in this new sense. I put a W because it's called Wasserstein. You have that here we had gradient psi equal D, and here we have gradient psi equal gradient D. That is in some ways very shocking, but it's natural. It's not the same kind of object because here the variation is a vector if you are in 2D, and here it's still a scalar. It's a vertical variation. So the objects are really very different. And actually, this is the right way to see it. So I'm not going to go into detail, but you can write it, at least formally, as a gradient flow in the Wasserstein space of where this is the space of probability measures. In some way, you can see it as an infinite dimensional manifold, and the tangent space in this manifold variation you can make on the density. They are not. You do not add things like in that you would do in L2, but you move things with L2 velocity fields, okay, horizontally in some way. So you have the norm corresponds to some kind of kinetic energy, and you end up with that. So I'm going to skip thing. Let me just say that it can be done. So here is more a few years work than a few minutes, but what you see here with the Stade de France and here a theater. Actually, it's nice, it's smooth, but something is bizarre. It goes too smoothly. And actually, it's usually I don't say that, but it's a very bad model. In fact, it's very interesting to study mathematically. What happens is that here, for example, the velocity of the guy accelerates when it goes to the door, which is normal because you have people pushing behind. In reality, it makes things bad. But in this model, it makes things go faster. and it's natural, it could be expected, but which makes this model not very realistic, because you do not have this capacity drop. You have this capacity anti-drop, meaning the more people you have, the more excited they have, the more quickly they will go, which is the contrary that happens in practice. So the microscopic model is actually a much better model for some mysterious reason, and I will use perhaps my last minutes to try to explain that. From my standpoint, the reason is that you have a bizarre Laplace operator underlying to talk about this. Pierre-Simon Laplace, who we're talking about. First, if you compare the microscopic and the macroscopic model, they are quite close. When the door is large, actually, it behaves a bit basically the same. But you can show that I will say a few words on that. If you consider the evacuation of a crowd, for some reason, actually this is not complicated to show. You have this velocity that is the projection on the cone of feasible velocity of the desired velocity. And when you have the desired velocity that is concentrating, meaning that it has a negative divergence, you have this Darcy-like. This is the saddle point formulation for those who are familiar with Darcy problem. It's a unilateral Darcy problem. And you can eliminate the velocity, and you end up with a Poisson problem on the pressure. This is the simple Poisson problem that will give you the velocity, the pressure inside the crowd. And the right-hand side, since the field is concentrating, is positive. So by the maximum principle, which was mentioned by Olivier, also is a bit different context, you have that P. It's not a Dirichlet problem, but it's Dirichlet and Neumann. And you have, but all homogeneous condition, you have a pressure that is positive, and you conclude that when you have someone at the door, since the pressure is positive, the guy is pushed, so it goes faster than he would if he were alone. So you do not have the capacity drop, you have the contrary. And the interesting question is this, it explains to you why the microscopic model is bad, but the question to ask is, the microscopic model was based on the same principle, and yet it is good. So there is something a bit shocking. And actually, when you compare the two models, you have two formally very similar things. This is the Darcy model from which you can extract your Poisson problem and the maximum principle. And you have the same, those are replaced by discrete operators. That this is a discrete divergence operator. This is, you can see it as a matrix or a discrete operator. And you can eliminate the velocity, and you get a B star that is, you can interpret as a Laplace operator. Okay? And those, and in 1D, actually, it works very fine. If you assemble this matrix, you find the matrix that some of you probably may know. This is the discrete Laplace operator. Everything works perfectly fine. And actually, in 1D, there is no paradox. Everything works fine, and all the models are the same. But if you are in 2D, that is the interesting dimension, you have something, you might expect a Laplace operator that would look like that one. When you have a contact between grains, you might imagine, that would be B star B actually, that you have a spring mass system, and you will get a Laplace operator from which we can write, is something, there is a PhD here that I monitored with someone in Paris on this wave equation on grains, assembly of grain. And this is a very standard Laplace operator. It has all the properties. The problem is that our Laplace, it acts on pressure, and pressure, they live on contact points. So the Laplace operator, it acts on the dual networks and not the primal. This is the primal, and this is the dual network, which is much less nice. It's not a planar graph. It's very pathological in some way. And you can show, in particular, that the associated matrix, it has very bad properties. For example, some extra diagonal terms, they are positive, they are negative. They should be, plus and minus. They should be negative. They are positive, which means that is a classic matrix numerical analysis. You lose the maximum principle. And an example, the simplest example that I find to show that is that when you have a fluid or anything, any continuous system, and you compress it from the outside, you have a positive. Any model, any reasonable model you take, you will have a positive pressure inside. If you take a discrete system that is made of 4 coins that are glued together, and you push them in this way, but you push more horizontally than vertically, you see that the pressure here, it will be negative. So you have a system, you compress it, and you have a negative pressure inside, you see, because you have this bizarre and this is quite typical of, and this is basically what explains that you can have these jams. This example of it is a jam. It should not exist because of the maximum principle, but because the underlying operator has very pathological property, it does actually exist. And here you have complete balance between the desired velocities and the action of interaction forces. And so I would just finish with this. You have also this paradoxical phenomenon that by adding an obstacle, you might improve the evacuation. Don't try to do that. It doesn't work always, but at least in this situation, it did work. So we have paradoxical effect. And I will stop on that. Thank you.
Thank you very much, Bertrand. It was very nice and interesting. Some question? Yes.
Do you think that when you're in the middle of a crowd and you want to try to escape, do you know what is the best path? The crowd is just crazy. They don't even know. They don't know where to go.
Yeah. Actually, when you ask to people when there have been a real problem with possibly with injuries, etc., when you ask people, usually they say, "I lost completely control of anything," and I think the best way would be just to keep losing control in some way. Do not try to struggle in some way, because struggle, if you want to oppose, you create pressure, and the pressure that adds. They make forces like have been estimated around 400 kilograms, horizontal forces, which crush your chest and.
But your models, I mean, your equations suppose that you know where you should go.
Oh, yeah, that's a nice question. Yeah, if you want to model real panic, that's something that you have to do. The mathematician alone cannot do that. You can put some kind of random things, but usually when you have real problem, they are at the MEC, for example, you have some structure. There are people, all of them want to go in the one direction, the other one, they want to go in this direction. Usually you have some structure. And when you have panic, usually there is some point. Panic creates panic, and it's quite structured. And so this approach, considering that all people want to go in the same direction, is not so unrealistic. Because you do like people around you. Yeah.
Well, there is a possibility if panic is not general, which is trying people to stop pushing. Trying to influence the people around you to stop pushing.
Yes, exactly. If you do that, if everybody stops pushing, then nothing happens. But as far as I know, it's completely impossible to do. What people think, it's basically if something happens, it's too late. It's too late. There is nothing to do, and you can do yourself. You can stop pushing yourself, but you will simply be crushed. Or you can try to avoid place where you might be crushed, like at corners or things like that. But
are you safer in the center or on the sides?
Well, it depends. For evacuation, I would say the center. You have some chances to evacuate more quickly. But yeah. It's easier because you have in some way mainstream and you profit the general motion. But in general, I wouldn't say what people say usually. That's why they want to avoid that upstream because.
Is there any optimal evacuation nozzle so that you have like a muzzle? Yeah,
that's a good question. We tried, for example, to optimize the shape of an obstacle. To that, but it's very sensitive and it depends on the model. So I think there is no general answer to this question. And this effect with the obstacle, it has not been proved experimentally. It has been observed for sheep, actually. But it's very difficult to perform real experiments with people. There are some experiments in Germany, but they find like a 12% improvement. So, and that would be the same for the shape. You can, if you take one model, a given model, I think you might find an optimal shape, but it's very sensitive with respect to the model you use or the experimental setting you have if you make experiments.
Panicking happens with cows in the films, in the Western films.
Yeah?
And there are some ways of checking them before they go to full panic.
Yeah, with the dogs and things. Yeah.
Yeah, so I enjoyed the talk. Is there any role for game theoretic concepts? I mean, have you seen some people doing that kind of stuff?
Yeah, we tried actually. I ran a PhD thesis on that a few years ago. We tried to include some. Yeah, that's a good point. Usually, you can consider that you are someplace, and your action is going to depend to what you expect people to do. And what we wrote is a model, but it's very messy, meaning that it's simple to write, but you at each instance you consider Nash equilibrium with respect, meaning that you consider the feasible velocities are the velocities such that if everybody does the same, you can do you do as good as you can. And you find, for example, you can in simple situation you have two people like they cross in a corridor, and this one wants to go this direction, the other direction. You have infinitely many possibilities that, and we can find. But for more than two particles, it's not even clear that a Nash equilibrium exists. If it mainly depends. What is very interesting, it leads to problem in graph theory. It's highly dependent on the structure of the graph. If you have a hierarchical graph, acyclic graph, then everything goes fine. There is no game actually. It's the civilized situation. The first one goes out and the other one they follow, and that's fine. But when you have cycles and possibly complicated cycles, then that's really a mess. And we were not able actually to identify the Nash equilibrium. But that's a good point. That's what happens all the way. What you do depends on what you expect people to do. Yeah.
Very interesting. Very interesting. I don't know if it is related with the discrete maximum principle. You know that there are a criteria to have the maximum principle in the discrete scheme, but there are some hypotheses quite strong,
which
and I think that you are exactly.
We do not have this
example are proving that.
And we do not choose it's not a discretization, as you understood, it's the model. So we cannot change the Laplace like it's not as if we were choosing a discretization algorithm. It's just the model that is
very interesting. Very interesting. Okay, we thanks again our lecturer.
Thank you.
And so this is the end of the meeting. It has been a very great pleasure, and we hope. Bien sûr.
Voilà, je voudrais vous remercier parce que j'ai passé une excellente journée. J'ai appris beaucoup de choses intéressantes et j'ai rencontré des gens que je ne connaissais pas. Le bonheur est total. Merci beaucoup.
Merci.
Yes, especially after the match of the football when. So we changed the imagine. So thank you very much for coming to Madrid.
La prochaine, ça sera la France 5, Espagne 4.
Ok.
Et on espère bien que ça sera bientôt. D'accord.
Bon, merci. Et à bientôt. Nous espérons. Merci. Au revoir.